How Voyager 2 escaped the solar system. Voyager 2 is the remarkable space probe that approached Neptune, the most distant planet in our solar system. It was the first spacecraft ever to complete the astonishing 4 billion kilometer journey to this mysterious gas giant, a world that was still largely unknown at the time. Neptune lies so far from the Sun that since its discovery in 1846, it has completed only a single orbit around our star. The true vastness of our solar system is almost beyond human comprehension, and navigating such an immense expanse is far from simple, governed by the complex laws of physics. Yet, in August 1977, Voyager 2 embarked on an extraordinary lifelong mission that would carry it through the solar system and beyond. Today, this pioneering spacecraft is over 20 billion kilometers away from Earth. But how did it manage to reach such incredible distances? In this video, we'll uncover the fascinating physics behind Voyager 2's journey and explore the ingenious systems it used to navigate the cosmos. Plus, stay tuned until the end for a chance to win an exclusive framed Saturn V print. How Voyager 2 used gravity assists. Back in the mid-1960s, a NASA engineer discovered a rare, planetary alignment involving the 4 largest planets, an event that only happens once every 175 years. This alignment offered a unique opportunity for a single mission to visit all 4 giants. Voyager 2 was tasked with this monumental challenge. To succeed, it had to thread the needle through space, executing 4 gravity assists to slingshot itself from planet to planet, and eventually break free from the Sun's gravitational hold. While the Sun constantly pulls on the planets, their rapid sideways motion keeps them in stable orbits. Without this speed, objects would simply be drawn into the Sun's fiery core. But if an object moves fast enough, it can outrun the Sun's pull and escape the solar system entirely. For Voyager 2 to achieve this, it needed extraordinary speed. The closer an object is to the Sun, the stronger the gravitational pull, like being at the bottom of a deep hill in the fabric of space. Escaping requires far more velocity from that low point than from a higher position. Since Earth is still relatively close to the Sun, Voyager 2 needed a huge boost. No rocket available at the time had the power to provide this alone, but thanks to that rare planetary alignment, Voyager could harness gravity assists as cosmic slingshots to gain speed with each flyby. A quick note on displate magnets. Speaking of magnets, those giant magnets on your wall? Just kidding! But if you love space art, you'll appreciate Displate's sturdy magnetic mounts that make displaying and rearranging metal posters a breeze. Whether you're into James Webb imagery, Voyager mission art, or my personal favorite, the NASA official Grand Tour collection, you'll find stunning designs that bring a touch of the cosmos into your home or office. With no tools required and less than 20 seconds to mount, displates are customizable, collectible, and built to last. Check out the link in the description to start your own space-themed collection and save up to 37% today. How Voyager 2 left our solar system. To break free from the Sun's gravitational grip, Voyager 2 had to exceed the solar escape velocity, about 42 kilometers per second at Earth's distance. Although it launched aboard the most powerful rocket available then, the rocket's contribution was only about 10 kilometers per second in delta V. That might seem small, but Earth itself moves around the Sun at about 30 kilometers per second. By launching Voyager in Earth's direction of travel, NASA cleverly leveraged this existing velocity to push Voyager's speed to roughly 40 kilometers per second relative to the Sun, enough to escape Earth's gravity and enter a vast orbit extending past Mars. Under ordinary circumstances, Voyager would have remained in this huge orbit indefinitely. But aiming for a gravity assist at Jupiter, it targeted the exact point Jupiter would occupy upon arrival, an incredible feat of precision. Despite the enormous scale of space around Jupiter, Voyager had to pass through a narrow 150-kilometer wide corridor, arriving at the exact location down to the nearest second, all while traveling at 10 kilometers per second. Missing this mark would have ruined the gravity assists at both Jupiter and Saturn. To achieve such accuracy, Voyager's navigation system had to know its position and velocity with astonishing precision. Voyager 2's navigation system. 5 sets of thrusters placed around the spacecraft allowed it to rotate along all 3 axes. This was crucial because Voyager's large antenna had to stay pointed directly at Earth for communications. The thrusters fired tiny millisecond pulses to rotate. Voyager at about 0.3 degrees per second attention. Slow but controlled motion taking 5 minutes to turn 90 degrees. Another set of thrusters could fire longer bursts to adjust speed and fine-tune trajectory over time. How did Voyager know where it was? A sun sensor on its antenna detected the sun's brightness, commanding Voyager to rotate until locked onto the sun, aligning its X and Y axis perfectly to Earth. To control the roll axis, a star tracker aimed 90 degrees away from the sun sensor, locked onto a known star's brightness. Sometimes these sensors were block-like when Voyager flew past a planet or turned to photograph targets. To maintain orientation during those times, Voyager relied on an onboard gyroscope, a spinning disc mounted on a 3-axis gimbal, which measured rotation changes with precision. This system allowed Voyager to maintain a fixed spatial orientation critical for navigation and communication. Tracking speed and trajectory. Knowing orientation wasn't enough. NASA also needed Voyager's speed and distance. They sent signals to Voyager and measured how long it took for responses, using light-speed travel time to calculate distance. Repeating this over time let NASA track Voyager's velocity. With these data points, NASA continuously plotted Voyager's trajectory against its planned path. If Voyager drifted off course, commands were sent to fire thrusters and correct its course. Thanks to this incredible system, Voyager reached its Jupiter target point just 1.4 seconds late and only 60 kilometers off course. Gravity assists and the final journey. As Voyager neared Jupiter, its speed slowed to around 10 kilometers per second, below the escape velocity there, about 18 kilometers per second. But Jupiter's powerful gravity pulled Voyager in and accelerated it dramatically, combining their velocities and boosting Voyager beyond the sun's escape velocity. From this moment onward, Voyager was set to leave the solar system. But its journey wasn't over. It performed 2 more gravity assists at Saturn and Uranus, making groundbreaking discoveries along the way. The last gravity assist was at Neptune, which was unique since no further planetary visits followed. Scientists wanted Voyager to fly close to Triton, Neptune's moon orbiting at a steep angle, requiring a sharp course correction. Instead of approaching from behind, Voyager came slightly ahead, passing over Neptune's north pole. This maneuver bent its path downward and slowed it enough to safely fly past Triton 5 hours later. Then Voyager began its eternal voyage into deep space. An epic 12-year journey. Voyager 2's epic 12-year odyssey transformed our understanding of the solar system and beyond. And now, for the moment you've all been waiting for, the winner of the stunning Falcon 9 framed print is Matthew Cole. Congratulations! If you didn't win this time, don't worry. The next video will feature another exciting giveaway. Next up, a chance to win the legendary Saturn V framed print. Just sign up through the link below and leave a comment predicting what will happen during Starship's first test flight. Thank you so much for watching. See you in the next video.